papers for you, so you don't have to write all this down. But I actually want to take this time to tell you something about the dangers of this. If you know, this is what I'm about to give you is probably what we covered over the course of about 3 days of Chem 1. But it's not going to be covered the same way. First of all, I gave you the notes. And secondly, when I give you notes, they don't pop up in a whole board at a time like this. They basically come up one sentence at a time, one line at a time, for a reason. And here's where the danger comes. You're going to go to college, you know, and I mean, granted, part of my job is to teach you and get you prepared for the AP exam, but that's not the main part of it. It really shouldn't be. It should be preparing you for college. And back to that, I used to always say this. I have you come up like that. I have all these things about one at a time because I know what happens when an entire board shows up. You just zone out. You don't pay attention. A lot of professors in college nowadays, they think they're doing a great job. They're doing you a great service. Some of them may even have to do it. But they put all of their PowerPoints on a paper. And like not the way I have mine here, where I've got them almost, they look like notes. There's actually 2 slides on here. But rather, they'll have like 6 slides on a page. You know, they'll be sideways. You've all seen that. If you've taken any courses in college, if some of you have, because you've got dual enrollment or whatever, many professors now, it's the new thing. It's not a new thing, I mean, but it's the big thing nowadays. They've been doing it for about 5 years at least, maybe 10, where people will just give you all the notes. Now, the temptation with that is not to pay attention, not even to go to class. That absolutely happens. I have all my stuff. Why do I need to go to class? I don't need to see this again. And when I'm talking, board's already up here, the other tendency is to do what Olivia's doing right now, zone out. She's not even looking at the board. And you know, because if a lot of you are like, you know, dogs. If I've got a treat in front of you, you know, and I'm holding that treat there, I got your attention. But once that treat's gone, yeah, they're going to go off and go smell themselves. So I need to keep your attention at all times. And it's very difficult to do. So a little warning for future reference. When you go off to college and a professor does give you all these notes and they all come up at once and you have them all in your notebook anyway, don't just assume you don't have to go to college. You don't have to go to classes. You could just basically look at that stuff and study and I'll be okay. Because it doesn't work that way. Matter of fact, this is a classic example is what I'm about to teach you right now. If all I did was say, okay, read this over and skipped ahead and went right to the examples, which, you know, there are too many boards ahead, but I went right to the examples like this board right here, and then ask you the questions on this board. Okay, what's this guy? Arrhenius or a Bronsted acid or base? Which is a conjugate acid or base? Is it a Lewis acid or base? You'd have no clue. You have absolutely no idea. Most of you, even when I get here, will have trouble getting this right. Okay? So it's important that you actually pay attention, although this is going to be a long class. I'm going over a lot of stuff, because this is a review of Chem 1 stuff. Everything on here, pretty much, there's a couple of exceptions you've seen before. All right, let's start with the different definitions of an acid. You will be asked to do this on my test for sure, and, of course, on the AP. What's the difference between Arrhenius, Bronsted, and Lewis acids and bases? Arrhenius. We have seen this before. We've actually seen Arrhenius and Bronsted definitions throughout this year, even in organic. You may remember in organic, we talked about carboxylic acids and amines being acidic or basic, and why they were that. I had a couple of demos where I had a bonus question. Something forming hydroxide ions. What did that make? It turned it pink. What did that mean for phenolphthalein? And just the last lab we did last week, where I did the qualitative equilibrium lab. And I added sulfuric, you added sulfuric acid and it changed orange or whatever color, I forget which color it changed. You had to explain it in terms of Le Chatelier's principle because the hydronium ion concentration was increasing. All of that stuff we've been seeing throughout this year, but I haven't really taught it. Now I'm going to review it. An Arrhenius acid, according to Arrhenius, an acid is anything that forms these guys, hydronium ions. That should look familiar to you. And a base is anything that forms these guys, hydroxide ions. That's all Arrhenius cares about. However, in order for this to be an Arrhenius acid or base, you've got to have something else around. What else has to be there in order for this to work? Water. You've got to have water for the acid to react with. You've got to have water for the sodium hydroxide to dissolve in. And what if you don't have water? Can it have an acid or a base? Absolutely you can. Let's talk about the Bronsted-Lowry definition. And here's one change already from my Chem 1 class. I've been noticing as I'm looking stuff up that the AP and this book does not just say Bronsted like I did. I just shortened it up and said Bronsted versus Arrhenius. It's actually called, and I don't want you to look at that, I've never heard of this before, Lowry, who's that? The Bronsted-Lowry definition is the same one. All right, it's the same thing we've been talking about. Anything that donates a hydrogen ion is going to be, or a proton, is the same thing. A hydrogen ion is a proton. You know why? There's only one proton and one electron in a hydrogen atom. If he loses his electron, he's a proton, and he's also a hydrogen ion. A base, and it accepts a hydrogen ion. So take a look at this guy. No water. Absolutely no water around. Yet the acid, look what he's doing. He is giving up an H to the NH3. You have to look at how this is working from left to right as we're looking at these guys. This H is being given to him and making NH4. He accepted the H. Well, he accepted the H. And what's left over is the chloride. He's the acid because he donated. He's the base because he accepted the H. Simple as that. We've seen that before. That should not be surprising either. Okay? Here's a new part. Brand new, really new, not just a new word. The Lewis definition of an acid and a base. Now, I will not, and I did not use this at all in Chem 1, and I will not use this much for us this year. And there's a couple of reasons why I won't. I won't ask it on my tests. It can be on the AP exam. I won't ask it on mine, but I'm going to show you what it is here, and we're going to talk about it a little bit more later. But I realized as I finally got here that I was going to have to cover this. I realized that next year I'm going to have to do things a little bit differently. This is the first year I've done it, and I have not covered how to do those difficult electron dot notations. They're called Lewis structures. Remember that? Lewis structures? There's a reason. You really kind of have to use the Lewis structures to see what's going on for a Lewis acid and base. Most of the time when it says to do these, if you're looking in a book, if you're looking online, it'll say, to figure out who's the acid or base, draw the Lewis structures first and see what happens. Because here's what Lewis says an acid and a base is. An acid is anything that accepts an electron pair, and a base is anything that donates an electron pair. You can only see those electron pairs if you draw out the electron dot notations, and that's a pain in the neck. And it's not a pain in the neck to do easy ones. Everybody and their uncle can do simple ones. I got one H, I've got an O over here like this. What's going to happen? I'm going to need, two H's, one here and one there, and that's the easy stuff. And we've done that for a long time. What I'm going to be doing, showing you how to do soon, when we get to the review for the AP exam, is how to do more difficult ones. That would explain, for example, why that is an acid-base reaction, believe it or not, according to Lewis. I don't see hydronium ions, I don't see hydroxide ions, I don't see an H being donated or accepted. Hard to say that that's going to be an acid or a base. But it is, if you draw it out like this, you will see, if I look at it like this, that the water molecule is actually donating an electron pair to this guy. Now, could you have drawn this? No, absolutely not. We only have the most rudimentary skills in electron dot notation drawing. We're going to get better skills at it. I'm not going to say good. We're going to get better at it, drawing more difficult ones with resonance structures, double bonds, triple bonds, and all that stuff, even polyatomic ions. I'm going to spend multiple days. I've already written those notes up, and it took me a long time, because I'll be honest with you. When I was in college, I basically faked my way through most of that. I only knew how to do the basic easy stuff. Really did. I mean, I'm not exaggerating. I was never very good at resonance structures, never very good at drawing electron dot notations that were difficult. The obvious ones, the ones that follow the octet rule, they were pretty simple. But I'm going to show you. Believe me, I spent a lot of time. I probably spent a week's worth of time, and it's going to take me a day or two, probably 2 days, to teach it to you. I've got the notes already written up. So that's what I'll be doing. As for right now, okay, for us, is what we're concerned about this chapter, okay, I won't ask you a lot of Lewis questions. I have some of the homework today, so practice it. But basically, it will make more sense to you once you're able to draw the electron dot notations. But you can see, even the ones I do as examples, you'll be able to see who is the in this case, the electron pair donor versus the electron pair acceptor. Okay, carbon, he's the acid because he accepted an electron pair. Notice it's the exact opposite. An acid, according to Bronsted, donates a hydrogen, accepts electron pair. You see? Now, that can get obviously very confusing. I'm not going to ask you on my test for this. But by the time the AP test comes around, I'm going to practice it a little bit, show you more about it over time. Okay, so that's a little review of Arrhenius and Bronsted acids and bases. There's two other concepts. There are two other concepts I want to cover: amphoteric and conjugate acid-base pairs. Neither of which you probably are both on the back side of that paper I gave you. neither of which you probably remember, so let's talk about it. First of all, amphoteric. That should be an easy word to figure out. Amphibian. Lives in both like land and water, right? Both. Can do both things, right? Could be either an acid or a base depending on the circumstance. It's a great example, a classic example of this is water. If I add hydrochloric acid to water, look what happens. The HCl donates as H, forms hydronium ions, left with a Cl. What is water in this case? He's a base. He clearly accepted a hydrogen atom, correct? A hydrogen ion. Look here. I take water and I add ammonia to it. What's he doing in this case? Yeah, water's given up an H this time. That makes the water an acid. Okay? Now, he can be either or. He can't be the same thing. He can't be both in the same reaction. So it depends on who he's reacting with. That's what amphoteric means. Now, conjugate acid-base pairs, I'm going to actually use these to illustrate those for you, and then we're going to do them all in the examples on that last, well, at the bottom of your paper there. We're going to do all those as examples. Conjugate, and then I'm going to give you time. You're going to have the rest of this period. I'm trying to do this pretty quickly for obvious reasons. Why am I doing this fast? Because it is all review. You say, well, I don't remember any of this stuff. I know. By the time I practice all this on the next board, hopefully you will. But I cannot spend the 3 days I probably spent originally teaching this to you. I can't do that now. We're just doing this as preliminary because this whole chapter is on acid-base equilibrium. And you got to know the basics of bases and the basics of acids and bases. Conjugate acid-base pairs are going to come up. What is a conjugate acid-base pair? Well, basically, it's what happens to a conjugate base is what happens to an acid after it does what it does, after it gives up its H. What's left is this guy. Do you see why? Obviously, he is an acid in this case. He's giving up an H. If I were to go backwards, the chloride would be accepting an H, wouldn't it? So this guy is the acid. This guy is what we would call the conjugate base of that acid. You see that? Okay. Same thing's true for this guy. If he's the acid, who's my conjugate base? In the reverse direction, after this guy gave up his H, who's the conjugate base? The OH. If he is the base in this case, which you all agree that he is the base, he is accepting an H, right? What do we call this guy in that direction? The conjugate acid. Why is he an acid? Because here, he's giving up that H to there to form water. You've got to be able to look at it both ways. Now, having said that, it's a definition of a conjugate acid-base pair, you should realize that the stronger an acid is, the weaker its conjugate base is going to be, and vice versa. The stronger the base, the weaker its conjugate acid, the weaker the acid, the stronger. It's always going to be the opposite. Let me explain why. We define a strong acid as an acid that really wants to lose his H. He wants to give all of it up. If I put in 1.0 moles of hydrochloric acid into my water solution, every bit of it becomes hydronium ions. Beautiful. That's what a strong acid does. But a weak acid, and you may remember this from Chem I, in a weak acid, if I put in, I used a light bulb. Remember when I used a light bulb? I used hydrochloric acid. I put a little thing of hydrochloric acid in the light bulb. Bright lights. Because it all, 100%, dissolved in solution. A weak acid, only about 4 or 5% dissolved in solution. It became ions. So it didn't conduct electricity. Remember the light bulb barely lit, if you remember that. We did it with orange juice. We did it with vinegar. They were weak acids, citric acid, acetic acid. Okay. Well, it makes sense that if this is a really strong acid and wants to lose hydrogen badly, what would I predict? That guy would be a really strong base? I predict he'd be a lousy base, because what does a base want to do? Except, he's not going to want to get that H back right after he just got rid of it. So that just makes sense. The stronger an acid, the weaker its conjugate base. Okay, so, like for example, sulfuric acid is a very strong acid. Okay? He gives up that first H, the first one in particular, very well. Okay? And he would give it up to ammonia. Okay? Afterwards, if I were to look at the reverse of this, what would I call this guy right here? What would he be? Conjugate base. He's already lost the H. What would this guy be? Conjugate acid. going back that way, because he'd be giving up that H to him in the reverse direction. So conjugate acid-base pairs, this would be the acid, he's his conjugate base. Those are the acid-base pair. This would be the base, conjugate acid. All right, and the strength of them, if I told you he was a very strong acid, you would predict him to be a very weak base, going back the other way. Okay? All right. Oops, I don't want that. Time for some practice on all of this, kind of thrown together. Okay, and you have all of the stuff at the bottom of that paper. We're going to look at it. It's also going to be up here. Let's do one at a time. I'll do the first one with you, and I'll give you more time to do your own for each of these until by the time I get down to the bottom here, you should all be good at this again. And like you were good at it back in Chem 1. All right. Start with this guy. I recommend this. Whenever you have a question like this, even if I don't care if it's asking for Arrhenius or Bronsted or Lewis, I always like to look for the Bronsted acid or base first. Who's donating or accepting a hydrogen? It's usually happening. If it's not, it'll be obvious. But if it is happening, you can have both. It's possible to have more than one thing at the same time. I like to look for Bronsted first because it's the easiest to see. There's an H. There he's not. What happened? What is water in this case? Yeah, so I'm going to call him a Bronsted acid. Okay? Because he went from H2O to just OH. He donated this H to him. Just did that. What does NH3 have to be? A Bronsted base. He accepted it. Okay? Let me ask you, continuing with that, what would I call this guy over here? The conjugate what? Conjugate base of water, and this guy would be the conjugate acid of NH3. Good, but I'm still not done. Last thing I got to ask myself is, do I also have an Arrhenius acid or base or anything? Yeah. Yes, I do. Arrhenius says if I've got OH ions formed, I've got an Arrhenius base. So who is the Arrhenius base? Another reason why we do the Bronsted first. Last class, and I'll bet you in this class, it's a 50-50 proposition about what you're going to say. I want you to think. Who do you think will be the Arrhenius base? Water or ammonia in this case? We obviously have OHs formed. One of those guys is an Arrhenius base. And it should be obvious if you think about it. Take a stab at it. What do you think? I heard both. I'm hearing about half and half out there. Half water, half ammonia, half NH3. He is the Arrhenius base. Let me tell you why. The NH3 is the Arrhenius base because for two reasons. I'm going to think of it this way. Two reasons. Well, he's also the Bronsted base. A guy can't be both a base and an acid in the same exact equations. That would be one good reason, right? Second good reason. If you go back, I don't want to go all the way back to that slide, but if you go back to the first slide, you'll realize that the definition of a Arrhenius anything is something that when you add it to water forms hydroxide or hydronium ions. Water can never be the answer. Water will never be the answer for the Arrhenius thing. Okay? Because water is a thing you're adding this stuff to form hydronium or hydroxide ions. Okay? In solution. There you go. Alright, so that's the best way to look at it. That's the way I like to think of it anyway. Let's try this one on your own. Try to do both the acid, the base, in terms of Bronsted, the conjugate acid and base, and then if there's an Arrhenius. Everybody agree he's a Bronsted acid? That makes sense? What does he have to therefore be? Bronsted base. Okay. What is the NH4? The conjugate acid of that base. And this guy is the conjugate base of the acid. Good. All right, what about Arrhenius? There are none. I do not have hydroxide or hydronium ions formed, so I don't have an Arrhenius anything. That's it. How about this one? I realize as I'm doing these examples, I probably should have had, because you know what I'm going to get for an answer when I ask somebody? Darren's probably looking at me now and realizing, if I ask somebody, why is he the Bronsted acid? Because he's on the left. You know, every single one of them, I happen to put the acid first. All right, that does not have to be the case. I hope you all realize that. The acid will not always be written first. Probably should have mixed those up a little bit, just to give, not giving that impression. Okay, Bronsted acid, Bronsted base. He must be the conjugate acid. And then it's the conjugate base. I think everybody would get that. But we also have an Arrhenius something because there's the hydronium, Arrhenius acid. Who's my Arrhenius acid? I will get people who will put down hydronium ions the Arrhenius acid. No, he's not. All right? The Arrhenius acid is who? Not water. I heard water again. It is not water. Water will never be the Arrhenius anything. All right? The Arrhenius acid is going to be the HClO3 because when you add him to water, you get hydronium ions. Okay, a couple more. This one, next one's really, really short and easy. You realize that this guy's not donating or accepting anything. He's just dissolving in water and forming hydroxide ions. That makes him a what? Arrhenius base. Arrhenius base because he's forming hydroxide ions, so he is a base, but he's not reacting, donating, or accepting any H's, or electrons for that matter. All right, I told you I wasn't going to do a lot with Lewis, but I am going to do this last one. Okay? I want you to see how you would have to, again, for a guy like this, you could clearly, there's no answer to the Arrhenius or Bronsted question, is there? Okay? Arrhenius acid, I don't have hydronium ions or hydroxide ions. Bronsted, I don't even have a proton hydrogen being transferred anywhere. Do I still have a chance for being an acid? Yes. And here's why, though. And I've got to draw him out. It makes it weird. And it makes it even weirder because one of the most common Lewis acids is the trifluorides, basically. Boron trifluoride, trihalides, I should say. Boron trichloride, trifluoride. They tend to be Lewis acids. And they do that partly because they're goofy. Boron and two other guys they don't follow the octet rule. They actually don't. There's actually weird stuff about that. If you think about boron trifluoride, when you go to draw him out, he looks like this. Okay, you don't have to draw him. I'm just going to... Actually, it wouldn't hurt if you did. You can draw him. He looks like that. Notice that boron does not have an octet. Did you notice that? He doesn't have an octet. Okay? Because what does each one of these dashes represent? Two electrons, a pair of electrons, right? All right, so that's what he looks like. Boron trifluoride looks like that. That's what he is. He's one of the few guys that doesn't do what you'd expect him to do. And we'll talk about why when I do those new notes on electron dot notations. All right, let's draw fluorine by himself. Here's fluorine. A normal fluorine atom, you all would agree, looks like that, correct? But since this is a fluoride ion, what does he have one extra of? Negative charge, right? He has an extra electron. It'll be right there, and therefore a -1 charge. Everybody good with that? If I were to draw these guys put together, I bet you all realize what he's going to look like. There's your F's, and your F's you already had, and then I'm going to draw them just for fun. I'm going to draw it without putting the dashes around it. I could just as easily put a dash there, but I wanted to emphasize the fact that fluorine is basically donating those electrons to boron. Now, that's the crazy part. Fluorine's donating. What we're so used to saying donating is acidic. But exactly, if you're donating electrons, that makes fluorine the base, okay? And this guy, the Lewis base, that is, Lewis base. And this guy, the Lewis acid. I don't have room, but you had to write Lewis acid there for this guy, okay? That's ugly. I realize that. We've not done Lewis ones. You're not going to see them on my, I won't worry about getting bad grade for my test on this because I haven't covered the electrons the way I should. Electron notation, Lewis structure the way I should. So I'm not going to, hammer you for that. But I have to cover it because you are going to see it. And you will understand it better when I do show you the new electron. Lewis structures, way to do it. Okay, good enough. Now your homework on these right there. I don't have them up there because I got to check your homework. I never did. You're going to pass that up right now. But copy this down because it's not going to be on the board for very long. That's your homework, and then we'll pass up your homework from last